Yeah, hi. So I'm a chemist in the physics department doing biology, so that's like kind of a weird thing. But yeah, I'm interested in photosynthesis, and photosynthetic systems are built out of pigments like chlorophyll A. And then these pigments are like coupled together by protein matrix, and they form something like protein-pigment complexes. And these lead to the formation of excitons. And excitons are simply the excited states of coupled systems. And then they form like bigger complexes, like these PS2 supercomplex. And they have like different parts. They have antenna complexes that absorb light, and they have a reaction center where the light gets transferred and you create energy. And I want to understand like how this energy, how these excitons move through the system. So there are a lot of problems, but I learned that you now call them not problems but challenges. So challenge number one is like it's super fast. Like we're talking about like hundreds of femtoseconds. So we need some kind of method that allows us to track these very fast energy transfer processes. And what we do is we use 2D spectroscopy. So we shoot like a bunch of laser pulses on our system. And then you get a map like that, like 2D correlation map that correlates excitation frequency with detection frequency over a time delay. So for example, we can look at this purple bacteria, and then we get 2D maps like that. And the interesting part are the cross peaks, the off-diagonal peaks, because that tells you excite the system at one part, at one frequency, but you see the energy after some time delay at another subsystem, at another frequency. And by following all these different peaks and analyze them, you can basically find all the different processes and see like how the energy moves through the system. So that's cool. That's already one challenge solved. But the problem is, and this is like part of my HFSP proposal basically, is that we also want to see differences in spatial resolution. So if you look at the photosynthetic membrane of this purple bacteria, there are like regions where you have a lot of LH2 complexes, and there are regions where you have a lot of LH1 complexes. And I want to understand, okay, can we probe the ultrafast dynamics at different spatial spots on this protein, on this bacteria membrane? So we need some kind of spatial resolution, and what you typically do is like fluorescence microscopy. You can go down to the single molecule level and resolve stuff like that. But we want to combine this with our 2D spectroscopy. So we want to measure like ultrafast exciton transfer spatially resolved. And what we do is we combine these two things and do like fluorescence-detected 2D spectroscopy. And that's one kind of technique which we call action-detected 2D spectroscopy. But there are like even more challenges, like technical ones, fundamental ones. And if you want to know like how spectroscopy works and how we face these challenges, please visit me at Poster 24, and I will tell you all about it.